So, how do we construct phase portraits? Numerical algorithms for solving general nonlinear differential equations are widely available, and we can easily construct the phase portrait by using computer simulations. For some systems, however, it is also possible to find the trajectories analytically. This means that we can find a function describing the trajectories, that is, a function, let's call it phi, that describes x2 as a function of x1, and some constant c, which will depend on the initial states. The pendulum without friction is an example of such a system. This ordinary differential equation describes the behavior of a pendulum with mass m. The length of the rod is L, and theta is the angle subtended by the rod and the vertical axis through the pivot point. There is a downward gravitational force equal to mg acting on the pendulum, where g is the acceleration due to gravity. Generally, there would also be some frictional force, but here we consider the case where there is no friction. Newton's second law of motion then gives that the behavior of the pendulum is described by this equation. For more details about modeling, you can have a look at section 121 in the book of Khalil. To obtain a state model for the pendulum, we first have to choose the states, and a natural choice here is x1 being equal to theta, the angle, and x2 being equal to the angular velocity, theta dot. The first thing we do is to write the system in state space form. The state equations are x1 dot, this is theta dot, and that is x2, which equals f1 of x1 and x2. And x2 dot equals minus g over L sine x1. And this is then our f2 function, which generally is a function of x1 and x2. So now we have the system in state space form, and we recognize this form from the general state equations that we wrote up earlier for second order time-invariant systems. The second thing we do is to find the slope. The slope of a trajectory is given by the derivative of x2 with respect to x1, and this is the same as the derivative of x2 with respect to time t divided by the derivative of x1 with respect to time t. And this from the equations is f2 of x1, x2 divided by f1 of x1 and x2, which in this case here is minus g over L times sine x1 divided by x2. Notice one thing, and this is what makes it possible to use the analytical method for this system. Notice that this equation for the derivative of x2 with respect to x1 is a separable differential equation. And hopefully you remember from calculus how to solve this. What we do is that we collect everything that has to do with x2 on one side and everything that has to do with x1 on the other side. Then we have x2 dx2 on the left hand side equals minus g over L sine x1 dx1 on the right hand side. And then we integrate both sides. The solution is then 1/2 x2 squared equals g over L cosine x1 plus some constant c that contains the initial values of x1 and x2. So we have found a function describing the trajectories of the system. If you need to brush up on separable differential equations, you may have a look in your calculus book or see Khan Academy. So for each initial condition, we get a constant number c, and the corresponding equation describes the trajectory of the system, and we can thus draw a family of trajectories, that is, a phase portrait. What I want you to do now is to pause the video and find the equilibrium points of the pendulum without friction. I hope that finding the equilibrium points went well. If so, you found that the pendulum has an equilibrium point at the origin, where the angle x1 and the angular velocity x2 are both 0. This corresponds to the pendulum hanging straight down. Also, the system has an equilibrium here, where the angle is pi and the angular velocity is 0. This corresponds to the pendulum being in the inverted position, standing straight up. The system also has an equilibrium point in 2 pi, which corresponds to the pendulum having rotated around one time such that the angle is 2 pi and then it is hanging still straight down. And if it rotates pi radians more and stays still, the angle will be 3 pi. And the pendulum will be straight up again, and so on. So the pendulum has a number of equilibrium points, all corresponding to the pendulum either hanging still straight down or standing still straight up. Having identified the equilibrium points, we move on to interpreting the trajectories that we have drawn. Around the origin, the trajectories are closed curves. Say that the initial value is here. The angular velocity is initially 0, while the angle is non-zero but not as high as pi, meaning that the pendulum stands out to the side. The gravity will of course make the pendulum move, giving it some velocity, and the pendulum will move out to the other side, where the gravity again will pull it downwards, giving it a velocity, and thus it will oscillate around and around, corresponding to the pendulum oscillating back and forth around the downwards position. And since there is no friction in the system, it will continue doing so for all time. If the initial velocity is sufficiently large, however, it may be sufficient to drive the pendulum exactly to the upwards position, and it then ends up in this equilibrium point, standing straight up and standing still. If the initial velocity is even higher though, the pendulum will pass through the upwards position and move around and around and around, achieving higher and higher angular value. See that the pendulum is in the equilibrium point here, where it stands straight up. Since this is an equilibrium point, the states do not change, so it will stay up here for all time. If it starts a little bit outside of the equilibrium point though, with a slightly positive angular velocity, then it can move around and end up in the exact upwards position along this trajectory. Or, starting here, it may oscillate around and around the downwards equilibrium point. So, by drawing a family of trajectories, constructing a phase portrait, we have determined the system behavior. We have found its qualitative behavior without having to find the system solution, x as a function of time t. Note that the time t is not given by the trajectories. It's not possible to know at exactly which time the system is at any point along the trajectory. So it's not possible to recover the solution x as a function of time from a trajectory. So a phase portrait does not give information about the quantitative behavior of the system solutions, but of the qualitative behavior. Here we use the analytical method to find the phase portrait, but this is only possible for certain systems and most often it's not possible. And then we can use a numerical solver instead. There are numerous computer programs for numerical solution of ordinary differential equations, and these can be effectively used to construct phase portraits. The first thing you do is to select a region of interest in the plane. Remember what I said earlier about why invariant sets are so central in the analysis of dynamical systems? It is because if the system state does not take off to infinity, it will eventually end up in an invariant set, and that is why we focus on the behavior in and around invariant sets. So the first thing to do when analyzing a system is to find its equilibrium points and possibly other invariant sets. Having found this, then you know which region in the phase plane that you should focus on, and then you can create a bounding box containing this region where the trajectories are to be drawn. The next thing to do is to select a number of initial state values inside this region. The simplest approach is to place them uniformly on a grid throughout the bounding box, but you will see that an evenly spaced set of initial conditions rarely gives an evenly spaced set of trajectories, and it's therefore a better approach to select the initial points interactively, such that you can choose initial state values to cover the areas in the bounding box which have not already been well covered by previously plotted trajectories. And then you calculate and plot the corresponding trajectories, that is, the curves representing the solutions of the corresponding initial value problems. What you will see if the system has unstable equilibrium points or unstable limit cycles, and I will define what we mean by unstable later, but for now, what characterizes these is that the trajectories surrounding these will move away from them. And therefore it can be difficult to get a detailed phase portrait close to this. What you do then is to simulate the system backwards in time. By doing so, the trajectories will no longer move away from, but instead move towards the unstable equilibrium point or unstable limit cycle, creating a nice and detailed phase portrait close to this. So how do we simulate backwards in time in practice? Our system is described by the differential equation, the time derivative of x equals some function f of x. We reverse the time by defining the new time tau being equal to the negative of the current time t. Then d tau, of course, equals minus dt. And if we take the time derivative of x with respect to the new time tau, then this is equal to dx over minus dt, which is minus f of x. So we replace the original initial value problem with this one.